Okay, so today we're going to be talking a little bit about stoichiometry, lecture 26 in unit 3. And basically, this is the beginning of the unit. We're going to be talking about balancing reactions and just what stoichiometry is. So basically, stoichiometry, put simply, is the relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically in a ratio of whole integers. For this particular lecture, we're just going to be talking about whole integers, not the exceptions or anything like that. But before we get into stoichiometry, we need to learn how to balance reactions and talk about why it's important, why we about why the law of conservation of mass is important. So matter can't be created or destroyed, and the products and the reactants must have the same number of atoms before and after the reaction. So like we're going to see right here in this bottom equation, they both need to have the same number of atoms of each molecule on each side. So the aluminum needs to have the same number of aluminum on the reactants as in the products. So our reactions are always going to be made up of the reactants on the one side and the products on the other, like it shows down here at the very bottom. And then the chemical arrangements are going to change within the reaction, but the actual number of each atom, it needs to stay the same on the reactants and products. So the way we're able to do that is we're going to be able to put coefficients in front of each molecule. So as we see here, we're going to have 4 aluminum, 3 O2, and 2 AlO3. And that's just to keep all of our the number of atoms the same, just because nothing can be created or destroyed. We're not going to have a loss of atoms in these equations. And this is what's called just balancing equations. And basically there's 3 simple steps on how to do this. So first, a lot of times we're just going to be given the names of the reaction. So for example, we're in this one down here, we're going to have sodium chloride yields sodium plus chlorine. And so we have to write it out first. And then we're going to see when we do that, that it's not, there's going to be less chlorine on the left-hand side than the right. So we're going to start usually with the easiest element, which is just being the one that only appears once in the product and reactant. So as we see in this example, sodium appears once in the product and once in the reactant, as well as chlorine appears only once in both sides. So we could start with either one. And so we're going to choose coefficients to balance the other parts after that. And what's meant by that is just we're going to put coefficients in front and then multiply it by the number of atoms in that molecule. So to start, let's just start out with the sodium Na. We have 1 on each side of the reaction. Just ignore these coefficients for now. And then we look at the chlorine. There's only 1 chlorine on the reaction or the reactant, and there's 2 chlorine on the product. So what we need to do, we need to multiply the sodium chloride by 2 so that the chlorine can have 2 atoms on each side. But then once we do that, then we're going to have an imbalance on the sodiums. So we just need to put a 2 out in front of the sodium in the product. And then once we do that, then it's all balanced. And then stoichiometry, like I said before, if we go back a couple slides, it's just the relationship between the relative quantities of substances taking part in a reaction or forming a compound. And it's the ratio. And so it tells us how many moles are required to form a product, like how many moles of a reactant are required to form a product. So for example, we have 2 moles of aluminum react with 1 mole of iron 3 oxide to produce 2 moles of iron and 1 mole of aluminum oxide. So this is what stoichiometry is. It's once we get it balanced. So we're going to do those the 3 steps of balancing. We're going to write out a reaction, and then we're going to start with the easiest one first. All 3 of these elements are equal in simplicity for starting. So I just went ahead and did it for you guys. And then the stoichiometry happens right here, this middle step. It's where you get the mole ratios of everything. And then, so you have your moles of Al, and then let's say you're trying to get to your, find out how many moles of Al2O3 you're gonna have. So your mole ratio right here is just the conversion step that you can do to be able to, that's like your, that middle step that you need in every reaction when you're going from different molecules. So we're just gonna have a little bit of a practice here. How many moles of aluminum oxide can be formed when you have 0.889 moles of aluminum in the previous equation? So you could go ahead and look at this equation and find out how many moles we're gonna have based on what we're given. So we have 0.889 moles. You could write down the equation. Here's the equation, so you don't have to go back to the other slide. And then, so what we're gonna do, we're gonna start out with our 0.889 moles, and then we're gonna go do our dimensional analysis, and then use our mole ratio, going from the 2 moles of Al is equal to 1 mole of our Al2O3. And then that's our answer. So right here, we use our molar ratio. These can cancel out. This one, the 0.8, the moles of Al, they're all gonna cancel out. And so we're just gonna be left with 0.445 moles of Al2O3. And that's stoichiometry for you. And then going on, we can even do, as we're not always going to be given the amount of moles. A lot of times we're going to be given how many grams of a certain reactant, and then we're going to be asked how much of a certain product we're going to be making with that. So we're going to practice. It's basically the same principles. The only difference is we're going to just start 1 step earlier. So instead of having the moles, we're given the grams, the mass of it. So we can just use our molar mass to figure out how many moles we're going to have. So just to start, it's the same process. Step 1, you're just going to write the reaction. 0.32 grams of aluminum reacts with excess iron 2 nitride to form aluminum nitride and iron. How many grams of aluminum nitride forms with this 0.32 grams of aluminum? So we're going to write out our reaction. After that, we need to balance it because there's going to be, if you look, there's 3 Fe on this side, 1 Fe on this side, 2 nitrogen, 1 nitrogen. And then when you go over, you could start out with any of them you want. I just did the aluminum first. There's 1 and 1, but then you go to your iron, 3 iron. So I just put a 3 out in front of this other iron on the product side. And then there's 2 nitrogen and 1 nitrogen. So I put that 2 out front as the coefficient, and that requires me to put a 2 so that the aluminum balances out as well. And then, So like I said before, we start out with 0.32 grams of Al, and then we're going to use our molar mass to figure out how many moles we have, and then we can use our molar ratio to figure out how many moles of aluminum nitride we have. And then we go back to our molar mass of aluminum nitride to figure out how many grams of aluminum nitride we have. So if you notice right here, just some more dimensional analysis. We're just going to cross out the grams, cross out the moles of Al, cross out the moles of ALN, and we're just left with grams. Now, a lot of times you're going to just be able to, depending on what the problem is, if it's wanted how many moles of aluminum nitride forms, then you're just going to skip this last step. But in our case right here, it asks for how many grams of aluminum nitride forms. So we're just going to keep going until we get the correct unit, which is 0.475 grams of aluminum nitride. And then there's, with stoichiometry, with gases, it's a little bit different just because you can't measure the mass of a gas very easily, but it's pretty easy to measure the pressure, volume, and the temperature of that gas. So what we're going to do, we're going to use our ideal gas equation to find out how many moles we have, and then you're able to convert that back over to how many grams you're going to need eventually. So here in this question, we're given how this balanced equation, so we don't need to balance it, and then how many grams of sodium azide are needed to produce sufficient N2, which is a gas, to fill 48 times 48 by 25 centimeter bag to a pressure of 1.2 atmospheres at 15 degrees Celsius. So it might look like a lot, but if you just plug in all of these numbers into our PV equals nRT, it becomes kind of pretty simple. And so first we need to figure out our volume. So we're just going to multiply all these numbers out, and we get 57,600 centimeters cubed. And then that is going to be 57.6 liters. You just convert that. And then after that, you set your moles equal to PV equals RT. And that R is going to be 0.0206 liters per atmosphere. Then 15 degrees Celsius needs to be converted into Kelvin. So you just add 273.15 to that 15. And then once you do that, then you're going to get 2.92 moles of N2. Now it's N2 just because that's the gas that fills this capacity right here at that point. And then once you do that, then you just use your molar ratio, which is going to be 3 moles of N2 is equal to 2 moles of NaN3. And then you use your molar mass to figure out how many grams are needed. And then once you do that molar ratio down here, and your 1 mole of NaN3 has a molar mass of 64.99 grams. So that means that you need 126.5 grams to fill that space of the gas. So now we're just going to do a little bit of practice balancing these reactions. So it's pretty straightforward on this first one. The second one gets a little more difficult. So just remember when the steps for balancing right at the reaction. We have the reaction. We aren't given the states of matter on this. But let's just start out with aluminum because we have only one thing of aluminum on each side. So it'll be pretty easy to start there. So we have 1 on this side, 2 on this side, multiply it out by 2. We have 3 bromine on the left, the reactants, but only 1 on the product side. So we need to multiply that out by 3. And then once we do that, then we're going to have 2 potassium on the left side and 3 on the right side. And then, so that means we're going to have a little bit of a variation there. So we need to multiply it by 3 to get a common denominator. And then sulfate, once we multiply that out by 3, then it all comes together. We're going to have to multiply the potassium bromide by 6 so that we equal the 6 potassium on the left side, and that causes us to need to put a 2 out in front of the aluminum bromide so that we get the 6 bromide on both sides. And then after that, this is all perfectly balanced. You can use this equation for whatever you might need it for. Stoichiometry, your molar ratios, figuring out how many grams are required for a particular reaction. And then after that, we are going to do this next reaction. It's a little more sticky. And so let's start out with hydrogen, just because there's only 1 on the left side, and then 1 place that it says hydrogen on the right side. And both of them luckily are 2, so we don't have to do anything, but oxygen has 2 and 1 on the left side or right side. So we're just going to put a 2 out in front of the hydrogen, or in front of the water. And then also because of that, then we get 4 hydrogen after that. So then we're going to need to put another 2 out in front of the hydrogen. So then everything is balanced at that point up until the sulfur. And it's a little more difficult in sulfur because we're going to have 3 on the left side and 8 on the right side. So it's not going to divide super easily. We're not going to have, it's not perfectly aligned right now. And if we change 1 on the left side, then we're going to have to change a bunch on the right side, and it's just going to be going back and forth. So what we can do instead, we can set this S8 equal to the S3. And by putting a coefficient of 3/8 in front of the S8, so then we get 3. But when we do that, then like we said at the very first slide, these coefficients need to be whole integers. They can't be 0.375, they can't be 1.5. So we're just going to multiply it out by this common number to get everything into whole integers. And in this particular equation, it's going to be 8 because we have 0.375, and the lowest number that we'll multiply out is 8. And once we do that, we multiply not only this 0.375 out by 8, but the 2, the 1, and the other 2. So when we do that, we're going to get our 16 moles of H2S, our 8 moles of SO2, 3 moles of S8, and 16 moles of H2O. And that is perfectly balanced. There's 32 hydrogen on the left side, 32 hydrogen on the right, and 16 oxygen on the left, 16 on the right, 24 sulfur on the right, 24 on the left. Everything checks out. Law of conservation of mass applies right here. So we're just going to have some practice from from balancing to stoichiometry, same equations in the last from the last slide, but now we're just going to take it a step further. So we have 1.3 moles of aluminum bromide and excess potassium sulfate. So what we need to do in this is we just need to use our 1.3 moles of aluminum bromide, and we're going to just make it use our molar ratio going from 2 to 6. So when we do that, that's a simple reaction where we just get 1.3 divided by 2 times 6, just because our units are going to cancel out our 2 moles of aluminum bromide. And once we multiply everything out, we're going to get our 3.9 moles of potassium bromide is formed. And then on this next one, 145 grams of dihydrogen monosulfide is reacted with excess sulfur dioxide. How much water vapor can be formed from this particular reaction? So we're just going to do 145 grams is what we're given. And then we use our molar mass of dihydrogen monosulfide, and that is 1 gram, or 1 mole is going to be 34.065 grams. And then we use our molar ratio down here as well, just because we need to convert it over to our H2O. So our 16 moles of H2S is also equal to our 16 moles of H2O. 1 mole, so then after that, we're just going to go to our molar ratio again, or not our molar ratio, our molar mass. 1 mole of H2O is 18 grams of H2O. And after we do that, then we're going to get 76.62 grams of H2O, or water vapor. And that is it for this PowerPoint. Thanks for watching, and keep watching to see how we apply for limiting reactants and that type of thing.